Welcome back, everyone. Now, in this lesson, we're going to bring back some attributes. We're going to be talking about graphing, and then we're going to incorporate even more limits, and we're going to bring in inequalities. So for these first three problems, I'm not going to spend any time on these, but I do want to show you the graphs. I made these problems intentionally and very strategically, so I would definitely take some time, pause, or whatever you need to look over these three problems. These are some really good problems. But yeah, I'm just going to skip over these for right now, but definitely take some time when you can to look over them. So we're going to jump right into vertical asymptotes, holes, and limits. So we have the graph of f of x over here on the left side, and we have the graph of g of x over on the right side. So I'm going to start over here on the left side. So the graph of f of x is going to have a vertical asymptote at an x value of -1, and it's going to have a hole at an x value of +1. And then if I look at the whole value up here, if I write this as a coordinate, this would be the value 1, 3. So it's going to get closer and closer to an output value of 3. So just as a recap, anytime we mention output value, we're referring to the y value. So down here, we're going to be looking a little bit closer at limit notation. Now, what you're going to see that's going to be a little bit different is now we're going to have these positive and negative signs written in a superscript, which is kind of like an exponent. So those superscripts, the sign in the superscript is going to tell you what type of limit we're looking at. So in this case, if you ever see a negative in that superscript, that means we're going to look at a single-sided limit. But we're going to look at it specifically from the left side. And then if you ever see a positive written in that superscript, then what this is going to tell you is that this is going to be a single-sided limit from the right side. All right, so we're going to go look back at our graph, and we're going to look at these limits from a single side perspective. So the first one I'm going to look at is going to be at my limit as x is approaching +1 from the left side. So if I look at my graph as it approaches +1 from the left side, I'm going to start from the left side of 1, and I want to get as close to an x value of 1 as possible without actually touching it. And I want to see what is the output value that I'm getting really close to. Now in this case, from the left side, I'm getting really, really close to a value of 3. Now if I use that same idea, I'm going to use the limit as I approach 1, but from the right side. So same idea, as I get really close to an x value of 1, but from the right side, we're still getting closer and closer to the output value of 3. Now we're going to look at the limit as it is approaching -1 from the left and from the right. So my limit as it approaches -1 from the left side, we're going to be looking at the vertical asymptote. So from the left side, as I get closer and closer and closer to -1, when I follow my graph, we're getting further and further down, which means we're going to be approaching -infinity. So in this case, my limit is going to be equal to -infinity. And then we're going to look at my limit as it approaches -1 from the right side. So as I follow my graph on the right side, as I get closer to an x value of -1, then my graph is going further up and up and up, which means my graph is going to be approaching +infinity. So now we're going to use this kind of information to help us with the graph of g of x. So the graph of g of x, if you look at your graph, is going to have a vertical asymptote at an x value of 1. So now I want to write the left and right sided limit statements of g of x as the function's approaching the vertical asymptote. So from the left side, I'm going to write the limit as x is approaching 1, but from the left side. So I want a negative sign in that superscript. And then we're going to be doing the graph of g of x. And then when I look at my graph, from the left side, we're going to be getting closer and closer and closer to 1. But as I follow my graph, we're going to be going further down, which means my limit is going to be equal to -infinity. And then as I approach my graph from the right, So as I approach 1 from the right side, we're going to be going further up and up, which means my limit is going to be approaching positive infinity. So I want my limit as x is approaching positive 1 from the right of g of x, and that's going to equal positive infinity. So now we're going to use this logic to kind of help us with this next section. So for this next section, we're going to write the left and right side limit statements as x is approaching 2 for each of the following equations. So over here, if I look at number 4, we're going to be looking at the attributes of these rationals. So essentially what you're going to need to do is you're going to be filling out the same chart that we did up here, but we're going to be doing it down here. We just don't give you any information because we want you to know what to look for, and you have to know how to look for it. We don't give you a graph. We don't tell you anything. So if I look at my graph, we're going to factor and simplify it first if possible, which there's nothing I can cross out. So we're just going to dive right into the attributes. So the first thing is I'm going to look for any vertical asymptotes, which in this case is going to be bottom equals 0. So that's going to be at x equals 2. Then I want to look for any horizontal asymptote, which in this case, it's top heavy, which actually means we're not going to have a horizontal asymptote. Since it's top heavy, we're actually going to have a slant asymptote, or an oblique asymptote, as you may know it. So to find the oblique asymptote, we're going to do division, but in order to do division, I need to multiply this out and put it in polynomial form. So when I multiply it out, we're going to get x squared plus 2x minus 3, and that's going to be over a binomial of x minus 2. And then in here, because we're dividing by a linear, you can do synthetic. So synthetic's going to be easier, so I'm going to use the x value of 2, which you get from setting the bottom equal to 0. And then I'm going to use my coefficients in the numerator to find my digits over here. So for synthetic, my coefficients are going to be 1, positive 2, and then negative 3. So 1, positive 2, and then negative 3. So with synthetic, you're going to start by bringing down that first digit, so 1, and I'm going to look at my values diagonally, which means I'm going to multiply. Then when I look at my values vertically, we're going to add, and then diagonally multiply again, and you're going to keep repeating that pattern until you get to the very end, and then add, which means you get 5. Now this last value here, hopefully you remember, this is going to be your remainder, which means you're going to ignore it in terms of slant asymptotes. So when I write my equation of my slant, we're looking at an equation of 1x plus 4, which is just the equation y equals x plus 4. So for my slant over here, y equals x plus 4. So the next attribute I'm going to look for is going to be any holes, if we have any. And in this case, nothing simplified, so we're going to have none. Then the next attribute is going to be x-intercepts, which is going to be the top equals 0, which in this case is going to be positive 1 and negative 3. So x equals negative 3, positive 1. I like to put them in order, but that's just me. Okay, and then we're going to find our y-intercept. So now you're going to plug in 0 and then find out where it crosses the y-axis. So that's going to give us negative 1 times 3 divided by negative 2, which is going to give us positive 3/2. All right, and then those are the only attributes we're really going to need. We don't need the domain, range, and end behavior necessarily. It will help, but it's not required. So now I'm going to go ahead and draw my graph. I would recommend giving yourself plenty of room towards the top of your graph. Okay, so when I get here, I'm going to start by plotting my asymptotes. So I'm going to do my vertical asymptote, which is going to be at 2. And then we have a slant asymptote, which is going to be at y equals x plus 4. So that's going to be, well, let's actually do these attributes first. So because we're not on an actual grid, you do need a label. So this is going to be a horizontal asymptote at 2. And then we're going to do the y-intercept, which is going to be at 0, 4, which I'm going to say is about up here. And then an x-intercept would be negative 4 to 0. So my slant asymptote is going to pass through those 2 points. I'm going to attempt to draw a line. Drawing is very hard. I'm going to extend this, so as you can maybe see why I told you to give yourself some room at the very top. Maybe you can see it now. Okay, and then make you dashed. All right, so now that we have the asymptotes, now we're going to plot any intercepts. So we have x-intercepts at -3, which is going to be a little bit to the right. So that's going to be -3, 0. Then we also have 1, 0. And then we have a y-intercept at 0, 3/2. Now, based on this information, because I'm going to have a branch of my rational on the bottom left, my other branch is going to be on this top right section over here. So when I draw, hello, go back over there. So when I draw, your rational in this case is going to look something like this. So now that I have my rational graph drawn, now we can go back to the original equation or the original question, and we're going to look at the limit as it is approaching 2 on both sides. So in this case, 2 is going to be an asymptote. So one thing I forgot to mention, which is actually super important, so oops, shame on me. So I'm going to go back up here. So I'm going to actually reference some information that we did over here. So my limits as it is approaching a value, and then if it equals a value, that actually tells you it's going to be a whole. So in this case, limit approaching if it's approaching a whole, then your answer for your limit statement is going to be a specific value. However, if I have a limit approaching a vertical asymptote, what's going to happen here is your limit is going to be going towards your infinities. Now, it's going to be up to you to determine which of the infinities. So am I going towards positive infinity or am I going towards a negative infinity? That's going to be part of what you got to figure out. So I will say, if your limit that you're trying to evaluate is a vertical asymptote, you're going to have to find these attributes so that you can figure out if it's going to be going up and down on whichever side. But if it's approaching a whole, then your attributes are going to be much easier because we're just going to have to plug in a value and find a value. So there's not as much, I would say, opportunity for mistake. All right, so looking down here, back to this one, we're going to be evaluating the single-sided limits as it approaches 2. So if I look at my graph, as I get closer to positive 2 on the left side, I'm going down indefinitely, which means I'm going to go towards negative infinity. So my limit as x is approaching positive 2 on the left side of f of x is going to equal negative infinity. And then my limit as my x value is approaching positive 2 on the right side, it's going to be going up indefinitely, which means my limit as x approaches 2 from the right side of f of x is going to be approaching positive infinity. So this is what we wanted to know. So with that, now we're going to look over at 5 and 6. So with 5, if I look at my equation here, notice how your x minus 2's are immediately going to simplify. So these are going to cross out, or rather, they're going to simplify. So your equation that we have left is going to be just x plus 4 over x minus 3. So what that tells me is that when I approach 2 on this rational, I'm going to be approaching a whole. So if I'm approaching a whole, what that tells me is I'm going to be approaching a value. So I don't necessarily need to do all my graphing, I just need to plug in. So for this equation, I just need to evaluate what g of 2 is. So g of 2 is going to be 2 plus 4 over 2 minus 3, which is going to be 6 over negative 1, which is going to give me negative 6. So I'm going to have a whole at the coordinate 2, comma, negative 6. So my limit statements, so I'm going to have the limit as x approaches positive 2 from the left of g of x is going to equal negative 6. And then my limit as x is approaching positive 2 from the right side of g of x is also going to be equal to negative 6. So now looking over at number 6. So once again, we're going to factor and simplify. It's already in factored form, so I'm good. So I'm just going to focus on simplifying. So the x minus 2's are going to cross out here in the top, and then we're going to have one of them cross out in the bottom. So that's going to leave us with x minus 4 over x minus 2 times x minus 1. So what's going to happen here is because 2 is going to be a vertical asymptote in this case, then we're going to have to actually draw out our graph, which I kind of just spoiled what a surprise was supposed to be in a little bit, but surprise. So we're going to start with the attributes. So vertical asymptotes are going to happen at an x value of 1 and 2. And then we're going to look at horizontal asymptotes, which in this case, it's bottom heavy. So y equals 0 is going to be the horizontal. We're not going to have a slant asymptote in this case. So for holes, x minus 2 crossed out. So the math says we're going to have a hole at 2, but we have a vertical asymptote at 2. So what you have to think about is it going to be a vertical asymptote or is it going to be a hole? Which one kind of supersedes the other one? So in terms of rationals, what you're going to have to remember is whenever this happens, a vertical asymptote trumps over any holes. So in this case, because that hole is actually really a vertical asymptote, in this case, for holes, you're actually going to have none. So now we're going to find x-intercepts, which is going to be the top equals 0, which is going to happen at an x value of 4. And then we're going to find any y-intercepts, which y-intercept is going to happen when you plug in 0. So it's going to be negative 4 over negative 2 times negative 1, which is going to be negative 4 over positive 2, which is going to be negative 2. So I want a y value of negative 2. So now I'm going to do a little makeshift graph. Try to give myself plenty of room. I think that's good. All right, so start with your vertical asymptotes. So it's going to happen at 1 and 2. And then we have a horizontal asymptote that's going to happen at y equals 0. So now I need to do my intercepts. So based on my intercepts, I'm going to have an x-intercept at 4, which is going to be over here, about. Whoops, I didn't label. X equals 1, x equals 2. And then we have 4 comma 0. There we go. And then my y-intercept, which is going to happen at negative 2. So that's going to be about down here, according to my scale. So based on this information, I still don't really have a ton of information as to what's going to happen on my graph. There's still a bunch of variations of the graph that could happen. So because I need more information, I am going to have to do a sign chart. So I'm going to move this up here a bit. And then we're going to fill in a sign chart down here. So as a recap for any sign charts, you're going to have to include any vertical asymptotes, x-intercepts, and then any x values of holes. Wow, my handwriting is terrible. There we go. So if I look at my graph over here of what I have so far, ask yourself, how many tick marks am I going to need on my sign chart? Well, I have an I have a vertical asymptote of 1, so that's a tick mark. Vertical asymptote at 2, another tick mark, and an x-intercept at 4, which is another tick mark. So I don't need the y-intercept on my sign chart. I just need these values. So when I draw my sign chart, 1, 2, and 3. So I'm going to label as 1, 2, and 4, but underneath each of these, just to go ahead and get in the habit of it for rational inequalities when we do that later, I'm going to go ahead and put the attribute that it corresponds to underneath. which I promise that will help you in the future. All right, so once I have my sign chart, now I'm gonna find some test values. So test values, I'm gonna plug in some, let's do 0, 1.5 or 3/2, and then we'll do 3 and 5. So I'm gonna plug these values into my simplified equation up here. So plug in 0. 0 is gonna give me negative, 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 which 3 negatives give me a negative. And then plug in 1.5. So that's gonna give me negative, negative, positive, which is gonna give me a positive. And then plug in 3, which is gonna give me negative, positive, positive, which is gonna give me a negative. And then I'm gonna plug in 5, which is gonna give me positive, 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 which is gonna give me a positive all the way around. So your sign chart is gonna tell you a ton of information. So what this really tells you is from negative infinity to positive 1, this whole little area over here, which is gonna correspond to this area because we have to be negative. So the first part of my rational is gonna look something like this. Well, I can do better. I want it to get closer to my, oh my gosh, I cannot draw. I want it to get closer to my vertical asymptote, but that's okay. And then between 1 and 2, I'm gonna be positive, and I don't have a change in sign, which means I have to stay above the x-axis, which means this is going to be kind of parabolic in shape, or that U-ish shape. And then from 2 to my x-intercept of 4, I'm gonna be negative. So in this area, I'm gonna be down here, essentially is what that's telling me. And then what happens here is we have a sign change when I get to that x-intercept, which means we're gonna cross at 4. So your graph is gonna do something like this. So now that we have our graph, now we can determine what's gonna happen at 2, and we can do our limit statements. So what's gonna happen here, so my limit as x is approaching 2 from the left side, we're going up indefinitely. So my limit as x approaches 2 from the left side, and this is h of x, that's gonna equal positive infinity. And then my limit as x is approaching 2 from the right side of h of x, that's gonna equal negative infinity. So here's your limit statements for this one. So these are some really good problems. So now we're gonna kind of take it a step further, and now I'm just gonna give you limit notation, and you're gonna have to write the equation of a rational. So we're gonna go a little bit backwards. Instead of giving you the equation and you give us limit notation, now we give you limit notation and we want the equation. So we're gonna really capitalize on this information up here. So if you have a limit approaching a whole, then it's going to give you a value for its output. And if I have a limit approaching a vertical asymptote, it's gonna give you the infinities as your output. So with that, if I look at this first set of limit statements, we're looking at the limit as it approaches 3 from both the left and the right, and then it's gonna give you a value of 5. So what this tells you is that this is going to be a whole. And then if I look at the next set of limits, so we're looking at the limit as it approaches 1 from the left and then from the right, and then we have a negative infinity and a positive infinity. So as I approach a value and I get the infinities, that tells you we're gonna have a vertical asymptote. And next, then I give you the limits as they're approaching negative infinity and positive infinity, and then we're gonna be equal to a value. So what happens here is this is actually going to be referencing the end behavior. So with the end behavior, this is going to be following your horizontal asymptote, which in this case, my horizontal asymptote is gonna be 1. And if we have a horizontal asymptote at 1, what this tells us is that your rational is an even degree. Meaning it's not top heavy, it's not bottom heavy, it's gonna be an even degree. So for example, if I had my end behavior limits, if these were saying 0 and 0, then that would tell me my horizontal asymptote would be 0, which would mean that that would be bottom heavy. And then if I was approaching, say, negative infinity and positive infinity, then that would be a slant asymptote, which means I would be top heavy. So that end behavior here is going to be very important. It's going to tell you a ton of information. So starting off, we're going to be working with our attributes. So I'm going to start with the vertical asymptote, and then I'm going to also need the horizontal asymptote, and then I'm also going to have any holes. So the vertical asymptote I know is going to happen at an x value of positive 1, and the horizontal asymptote, which we know is going to be a y value of 1, and then we're going to have a hole at an x value of 3. So the next thing I want to do is I want to kind of give myself a visual of what exactly it is I'm doing. So my vertical asymptote at 1, then a horizontal asymptote at 1, and then I'm going to have a hole at the coordinate of 3, 5. So that's going to be, we're just going to say approximately up here. So because I'm going to have a coordinate in the top right section of my rational, then the other segment would be in the bottom left. So what's going to happen is my rational is going to look something like this. Emphasis on the fact that this is a rough sketch. Heavy emphasis on rough. So ask yourself, based on these attributes over here that I have on the left side, what do I subtly have over here that I did not include over here? So when constructing a rational, your vertical asymptote is going to be written on the bottom, holes are going to be written in the top and the bottom, but what other attribute do we need in order to construct a rational equation? Well, we also are going to have a mystery x-intercept. So this unknown x-intercept is actually going to be pretty important. So what I'm going to do is I'm going to include the attribute of an x-intercept, and I'm going to say this is going to be equal to some unknown value that I'm going to call just the letter n. You can really use any letter, just not x or y, but yeah, you can use anything. So I'm going to build on these characteristics, and I'm going to use these characteristics and attributes to actually construct my rational function. So with my rational function, if I have an x-intercept, a vertical asymptote at x equals 1, then that's going to turn into x minus 1 as a binomial, and then that's going to be written in the bottom. Okay, and then if I have a horizontal asymptote, what this tells me is that this is an even degree. And then for holes, as an x value of 3, that's going to be rewritten as x minus 3, and then that's going to be written in the top and the bottom. And then if I have the binomial, or not binomial, if I have an x-intercept of an unknown value, which I'm just saying is n, I'm going to rewrite this as x minus n, and then that value needs to be written in the top. So what's going to happen, so I'm going to construct my rational. I'm going to have x minus 1, which is my vertical asymptote, written in the bottom. Then I'm going to have x minus 3 in both the top and the bottom, which represents the hole. And then I'm going to have x minus n, which is going to represent our unknown x-intercept, which that's what we're trying to find. So once we find that x-intercept, then we can actually have our equation written. So first thing that you're going to do here is you're actually going to simplify. So when I simplify, that's going to leave me with just x minus n over x minus 1. So when you get here, you need to plug in a known coordinate. So the only known coordinate that we have that we know for sure is going to happen is going to be the coordinate of the hole. So we're actually going to reference that coordinate for the next part. So we have a hole at 3, 5. So I'm going to plug that in for my x and my y value respectively and solve it for my n value. So I'm going to have 5 is going to be equal to 3 minus n over 3 minus 1. So when I solve this, now we're ready to solve it for n. So I'm going to have 5 is equal to 3 minus n over 2. Multiply the 2 on both sides, so we're going to get 10 equals 3 minus n. Subtract the 3 on both sides, so we're going to have negative n is equal to 7, which means my n value is equal to negative 7. So that's not our final answer, but we definitely need that for our equation up here. So what I'm going to do is I'm actually going to copy and paste this. Now I'm going to do this next part step by step. So when I plug in that negative 7, so that's going to leave me with x minus 3 parentheses x minus negative 7. And then that's going to be over x minus 1 parentheses x minus 3. Now, of course, minus that negative, that's going to turn into addition. So your final equation will actually be x minus 3 parentheses x plus 7. And that's going to be over x minus 1 times x minus 3. So that's going to be the equation we're looking for. All right, now with number 8, we're going to follow the same steps, but this one's going to have a bit of a curveball thrown at you. So with this one, starting off, we have the limit as it approaches negative 2, and that's going to be equal to 4. So because it equals an output, this tells me that this is going to be a hole. And then my next information that I need is going to be the fact that we're approaching negative 1 from the left and then from the right, and then we're going to equal infinity on both sides. So this is actually kind of the curveball right here, the fact that it's positive on both sides. So I'm going to get to that in a bit, but this tells me I'm going to have a vertical asymptote at an x value of negative 1. And next, we're going to look at your end behavior limits. So in this case, that's going to tell us that we have a horizontal asymptote at y equals 0. And then because the horizontal asymptote is y equals 0, this tells us that it's going to be bottom heavy. All right, so now let's find our attributes. So vertical asymptote. So that's going to be at x equals negative 1. Then a horizontal asymptote in this case is going to be y equals 0. We're going to have a hole at an x value. Is it negative 2? Yep. And then we're always going to have some mystery x-intercept that we're going to have to solve for. So I'm going to always rewrite this or label it as just x equals n. So just like before, I'm going to go ahead and construct my rational. So if I have a vertical asymptote at x equals 1, that's going to turn into x plus 1, and then that's going to be written in the bottom. And I'll just write b for bottom. And then for a horizontal asymptote y equals 0, this tells me it's going to be bottom heavy. And then for the hole, that tells me I'm going to have a binomial of x plus 2, and then that's going to be written in the top and bottom. And then my x-intercept, which is unknown, is going to be x minus n, which we're going to write that in the top. So when I write, so we're going to have y equals. So in the bottom, we're going to have the x plus 1. And then top, we're going to have x plus 2. That's a 2. And x plus 2. And then in the top, we're going to have x minus n. Now, one thing I want you to realize when I write this out, is that consistent with having something that's considered bottom heavy? No, this is technically an even degree. So this does not work with this. So we're gonna have to go back and make an adjustment. But that adjustment, you're actually gonna pay attention to this curveball. So you're looking here. So I'm actually gonna sidebar this for a second, and we're gonna come down here. So what's gonna happen is I'm gonna have these two graphs. So the graph on the left is just gonna be a typical rational function, just just 1 over x. So what needs to happen is we want our graph to end up going up and up on both sides. So you wanna ask yourself, how do I make that happen? So really, I wanna do something to my entire graph that's going to make the positive side stay positive, but then I want to bring this negative component, this negative branch, I want to bring that up here. So you have to ask yourself, what can I do to an equation that would keep it positive but make all negative values positive? Now what we're going to do to it is you're going to square it. So meaning, what's going to happen over here for the vertical asymptote at x equals 1, when I turn that into a binomial, that would be x plus 1. But if I don't square it, then we are going to have a typical rational where it's going to go up and down on both sides. But if I were to square it, that's what's going to make it go up and up. So what you're going to do to your equation over here, your vertical asymptote, in order for it to be consistent with the up and up nature, we're going to do squared on that binomial. And once I square it, now it's considered bottom heavy. Now I'm good. So this is what I want to work with. So once again, I'm going to simplify this equation. So when I simplify, we're left with x minus n over x plus 1 all squared. And then I want to plug in the value of the whole, which is going to be negative 2 comma 4. So 4 equals negative 2 minus n over negative 2 plus 1 squared. So negative 2 plus 1 squared is going to give me negative 1 squared, which is just going to turn into positive 1. So I don't even need the denominator. So that's just going to be 4 equals negative 2 minus n, which is going to be a negative n equals 6, which is going to be n equals negative 6. So when I plug in, so this is going to be x plus 2, then x minus a negative 6, which is going to turn into x plus 6, over x plus 1 squared times x plus 2. So this is your equation. Okie dokie. So I'm going to move that up here. All right, and then 9 and 10 are really similar to what we just did. It's just going to be writing the graph, or not writing a graph, filling in a graph based on the following attributes. So I'm going to skip over that. Oh, one thing that is not on here that should be on here is this one is going to have a horizontal asymptote of y equals negative 3. And then this one over here that I added in, I wrote it as a description, but I'm going to just write it as a limit statement. So my limit as x is approaching negative infinity of f of x is negative infinity, and my limit as x approaches positive infinity of f of x would equal positive infinity. So I just added in the in-behavior stuff to these two questions. So on the newer version of the notes, it should have those two descriptors. So we're going to move down to 11. So with 11, now we're going to graph, given the graph of a rational function, now we're going to write the equation. So this, we're going to find the same attributes that we did before. So vertical asymptote, we also need a horizontal asymptote. We're going to need any holes. And then we're also going to need x-intercepts. So when writing equations, these are the 4 attributes that you need to focus on. So vertical asymptote in this case is going to happen at an x value of 2. And then a horizontal asymptote in this case is going to happen at a y value of -1. And then a hole is going to happen at an x value of +4. And then we're going to have an x-intercept at an x value of 3. So what's nice about these problems is I just need to look at a graph of the attributes, and especially they give us the x-intercept. Whereas up here, we had to go look for it and solve for it. So these should be a little bit easier than limit notation ones, hopefully. So now we're going to do the same thing that we did before. We're going to use the attributes to construct our graph. So if I have a vertical asymptote of x equals 2, I'm going to write that as x minus 2, and then that's going to be written in the bottom. If I have a horizontal asymptote of y equals -1, that tells me it's going to be an even degree. However, an even degree, my handwriting is so bad, an even degree where the leading coefficient is going to be -1. And then for the whole, we're going to be x minus 4, but then that's going to be written in both the top and the bottom. And then for the x-intercept, that's going to be x minus 3. And then that's going to be written solely in the top. So when I write out my info, or write out my equation rather, so this is going to be x minus 2. And then we're going to have x minus 4 in the top and bottom. And then in the top, we're going to have x minus 3. And then because we have the even degree with a leading coefficient of -1, you're going to have to add in that negative in the very front. And then that would be your answer. So what I want to do on this one, so yes, this is your final answer for this one, but now I just want you to kind of watch and listen as I do this next part, because I want to kind of alter this problem a little bit. So my alterations are going to change up the problem a bit. So really what I want to do is I want to change up my horizontal asymptote. So let's say my horizontal asymptote, give me just a second, let me make some adjustments. So let's say the horizontal asymptote, let's say I change it to a +3. So that means my leading coefficient would have to be a 3, which means I need a 3 out in the front of my rational. And then let's say I have a a horizontal asymptote, let's say at -2/3. So that means my leading coefficient needs to be a -2/3, which means I'm going to need a -2 in the numerator, and then I would need a 3 in the denominator. So whatever the horizontal asymptote value is, that's going to be your leading coefficient for your rational, if it's something other than 1. And then another question I was constantly getting is, well, what if it's 0? Then how do I put a 0 in the front? Well, if your horizontal asymptote is 0, then it would be bottom heavy anyways. So you wouldn't have to worry about something like that. Okay, so let's go back to the original. So this would be -1 with a leading coefficient of -1, which means we would have that negative. All right, and then 12 is going to be the same idea, so I'm going to let you guys try that one. 13 was supposed to end up on the homework, but somehow ended up on the notes. 14, we already did a very similar situation with the limits that we did up here with 7 and 8. And it also kind of incorporates 9 and 10 a little bit. So I'll let you guys try that one. And we're going to solve rational inequalities. So as we have done before, we've done sign charts. We're just going to use them more intentionally with inequalities. So you're going to be determining whether your values are positive or negative. And then before we actually dive into these algebraically, I'm going to do a graphical example. So the graphical example here is going to be a graph of f of x, and we're going to be finding the following intervals. I want to determine f of x where it's less than or equal to 0, where it's greater than 0, and when it's greater than or equal to 1. So in this case, if I want to find where it's less than or equal to 0, then that tells me I can equal an x-intercept. However, you want to ask yourself, the 3 values I put on a sign chart are going to be vertical asymptotes, x-intercepts, and x values of holes. So ask yourself, if I go to a vertical asymptote, if I want to go to -3, could I equal -3? No, because we have a vertical asymptote. If I go to +3, could I equal 3? No, because we have a vertical asymptote. So the key here, your big takeaway, is you can never include any vertical asymptotes or x values of holes. But you sometimes are going to include your x-intercept, and that's going to be contingent on the inequality sign. So in this case, because I can be less than or equal to it, this is a case where I could equal 0. So when I look at my graph, I want less than or equal to 0, so I want everything below the x-axis. So I want these two intervals here. So I want to write those in terms of interval notation. So that would be starting at -3 and then going until we get to -1. Now, if I look here at -3, that's a vertical asymptote. I cannot be equal to it, which means I need a parenthesis. But when I go to -1, that is a 0, which means I can be equal to it, which means I need a bracket. And then I have another segment, which means I need a union. And then we're going to start at 2 and then go until the vertical asymptote of 3. And then because 2 is an x-intercept, I can include it, which means I need a bracket at 2. And 3 is a vertical asymptote, which means it needs a parenthesis. So that would be my interval for number 8. And then I want to find the interval where it's strictly greater than 0. So I want everywhere that is above the x-axis. So I want the branch that's way over yonder. And I want the branch that's way over yonder. But then you also want to keep in mind we have this tiny little sliver right here that we need to include. Now in this case, you want to ask yourself, can I include my x-intercepts in this case? Well, no, because we're not equal to 0. So my interval here would be -infinity until -3, both with parentheses, union, -1 to +2, both with parentheses since we have to exclude the zeros, union, and then we're going to go from 3 to infinity. So that would be your interval for 9. And now for 10, now we're looking to see where it's greater than or equal to +1. But if you look at your graph up here, we have a horizontal asymptote at 1. So this is kind of a trick question. It's saying we can be equal to it, but we don't actually really equal it. And then a couple other students had pointed out to me, well, if you look really close over here, we kind of do cross it at 6. But I will say on assessments, we're going to make it pretty clear if it crosses a horizontal asymptote. So over here, we're just going to assume that it does not cross that horizontal asymptote. So over here, I want it to be bigger than or equal to 1, but in this case, it's just going to be those two branches on either side. So that's going to be from -infinity until we get to -3, then union, then +3 to infinity. So now looking at an actual, inequality. So now I'm actually going to do these algebraically. So what you're going to need for your inequalities is you're going to need your vertical asymptotes. We're going to need to find any holes. And then you're also going to have to know any x-intercepts. Now, these are the only values that you're going to need on your sign chart. So for vertical asymptotes, that's the bottom equals 0, and that's going to happen at -6 and +3. And then for any holes, nothing crossed out, so we're not going to have any. And then for x-intercepts, that is going to be when the top equals 0, which means we're going to do x equals 2. Now what we're going to do is we're going to create a sign chart, and we're going to mimic the sign chart that we did up here. So when I say mimic, I mean we're also going to label what types of attributes those values represent. So down here, I am going to draw my sign chart, and we're going to have 3 tick marks. So our first tick mark is going to be at -6, which is a vertical asymptote. And then we're going to have another tick mark at 2, which in this case is an x-intercept. And then the last tick mark, which is going to be at 3, which is a vertical asymptote. Now, I'm labeling these underneath because I have goldfish brain and I forget, and I don't want to get any of these attributes mixed up. So that's why I like to label them, but that's just me. So once you get your sign chart, now we're going to find test values. So -7, I'm going to test 0, I'm going to test 2.5 or 5/2, whichever, and then we're going to test 4. So I'm going to take these values and plug them in up here. So -7, so -7 minus 2, -7 plus 6 is negative, -7 minus 3, negative. 3 negatives make a negative. So when I plug in 0, we're going to get a negative, positive, negative, which is going to make a positive. And then when you plug in 2.5, we're going to get a positive, positive, negative, which is a negative. And then when I plug in 4, we're going to get a positive, 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 which is going to give you positive. So in this case, I want all the values that are greater than or equal to 0. So that tells me I can be equal to x-intercepts. So I want the interval from -6 to 2, and then from 3 to infinity. So when I write my interval, I want from -6 to 2, and because I can include an x-intercept, 2 is going to have a bracket, but -6 is going to have a parenthesis because it's a vertical asymptote. And then union, and then it's going to go from 3 to infinity. Now 3 is a vertical asymptote, so that's going to have a parenthesis, and then infinity always has parenthesis. So that would be your interval. So here are some extra problems for you. I would definitely do these when you get a chance. We are going to throw some curveballs at you when factors are going to be squared or whenever you just have a lot more factoring that you're going to have to do within those problems. But this is kind of the bare basics of what's going to be expected. So thanks for coming to my TED Talk. Make good choices.